Hi, discrete math students. Hope everyone's doing well. Welcome to day 2. We're going to talk about probability a little bit more, but focus on independent and dependent events. So I would encourage you guys to grab some paper, take some notes, and then try day 2's Google form. Okay, so first of all, a quick reminder on what does it mean for events to be independent. So if events are independent, that means the probability of one event is not going to affect another event's probability. So let's look at two examples to kind of explain that a little bit better. It's one example, two problems. So for this example, each situation determine if the events are independent or dependent. So for number 1, it says you flip a coin, then roll a fair 6-sided die. The coin lands heads up and the die shows a 1. So we have to think about the two events that are happening. There's event A, where you flip a coin. And then there's event B, where you roll a dice. And we're trying to determine, is you flipping a coin going to change the probability of you rolling a particular number on the dice? And the answer to that is no. There's no way that flipping a coin is going to affect how the dice roll happens. So these two events are independent. Now, if we get into something a little bit different, where it's not two different tasks that we're completing. So a box of chocolate contains 5 milk chocolates, 5 dark chocolates, and 5 white chocolates. You randomly select and eat 3 chocolates. The first piece is milk chocolate, the second is dark, and the third is white chocolate. This last part is just like extra information. You don't really need this. Kind of like up here at the top, knowing what the final result was isn't super important. What we care about are our events of selecting a chocolate. So the events are, event A would be selecting first chocolate. Event B would be selecting the second chocolate. And event C is selecting the third chocolate. So if we think about selecting the first chocolate, when we initially draw, there are 15 chocolates to choose from. And then after we choose that one chocolate and then we eat it, I would assume that we're not going to put it back in the box after we've eaten it. So when we pick that second chocolate, we only have 14 chocolates to choose from. Using the same reasoning, we only have 13 chocolates to choose from the third time, which means the probability of selecting any particular chocolate is going to be affected by what chocolate you picked the first time, because it's going to change our denominator when we're finding that probability value. So this is kind of going back to the idea of replacement versus not replacement. When we do not replace things, we are going to have dependent events because we're going to be changing the total number of possible outcomes. So for this one, our events are dependent. All right, so remember, if you have any questions on this first little part of the video, feel free to go to our collaboration document and ask there. All right, so our next part is if we know that events are dependent and we want to find their probability, then, and we're talking about the probability of more than one event occurring. So something like the probability of A and B. So if we know they're independent, then in order to find that probability, we're going to take the probability of A and multiply it by the probability of B given A has occurred. So this little symbol right here, remember, it means given. It doesn't mean that we're dividing. So let's take a look at what that would look like. So example 2, sorry about the typo. There are 8 shirts in your closet, 4 blue and 4 green. You randomly select one to wear on Monday and then a different one on Tuesday. What's the probability that you wear blue shirts both days? So we're talking about selecting shirts. I'm going to assume that we're not going to wear the exact same shirt 2 days in a row. We're probably going to wash it in between wears. So this is one where it's dependent because we're not replacing. So if I want to find the probability of wearing blue on both days, so the probability of blue and blue, that means I need to multiply the probability of a blue shirt times the probability of picking a blue shirt given we've already picked a blue shirt. All right, so what that looks like is the probability of a blue shirt. There are 4 blue shirts out of a total of 8 shirts. And then if we've already picked a blue shirt, there would not be 4 blue shirts anymore. There will be 1 less than that because we've already worn one. Same idea for the denominator. There will not be 8 total shirts that we're picking from anymore. There will be 7. So once we get this, we can multiply 4/8 times 3/7 and get a final probability of 3/14, or 0.2143, depending on how the question is phrased. All right, if you've got any questions about this section, so example 2, please feel free to add those to the collaboration document. We've got one more thing to look at together, and that is how do we tell if events are independent or not mathematically? So not just by like common sense reasoning, but sometimes we need to justify mathematically because we're not sure if one event affects the other. So kind of our 2 rules of thumb are, number 1, if events are independent, then the probability of A is always going to be equal to the probability of, we normally do it this way. We say the probability of B. I don't want to confuse people. So the probability of B is equal to the probability of B given A, which just tells me what we know already, that the probability of B occurring is not going to be affected by the fact that A has already happened. So one way that this rule shows up is looking at our statement of the probability. Hang on, let me just scroll back here. This probability statement right here. So if events are independent, then the probability of B given A is equal to the probability of B. So if events are independent, we know that the probability of A and B occurring is just equal to the probability of A times the probability of B. So statement 1 and statement 2 are basically saying the same thing. It's just the idea that this could be replaced in statement 2 if we were talking about dependent events, but we're able to put in that probability of B because the probability of B is equal to the probability of B given A. So places that this could show up are an example like this. So it says determine if A and B are independent, and it doesn't give us any information as to what those events are, so we're just having to use the math part of it. And we said that we know if events are independent, then the probability of A and B is equal to the probability of A times the probability of B. So with these numbers that they've given us, we kind of just have to check to make sure that that is correct. So we're going to plug in what we know. This is 1/25 is equal to 2/5 times 1/4. And essentially, we're trying to make sure that's a true statement. If it is, we know the events are independent. So 2/5 times 1/4 is going to give us 2 out of 20, which we know is not equal to 1 out of 25. So these events are dependent. If they were equal, it would be independent. All right, once again, if you guys have any questions, make sure you add those to the collaboration document. And then if you'll please go ahead and try that Google form for today to see how you do.